Last time we have seen that if V is a vector field along a curve gamma whose local coordinate representation is this, the condition of being parallel, that is a covariant derivative of V along the curve gamma equal to 0, is equivalent to a system of linear ODEs. And in order to solve it, we can use this existence and uniqueness smoothness theorem, because this system here has this structure, and we can prove the following theorem. This theorem is about the existence and uniqueness of parallel transport given a smooth manifold with or without boundary and nabla a connection in the tangent bundle. Then given a smooth curve gamma in M, T0 in the open interval I, and V in the tangent space to M at the point gamma T0, there exists a unique parallel vector field V along gamma, such that the value of V at T0 is equal to the given vector small v. If we prove this theorem, we can define the parallel transport of small v along gamma precisely for each T0, T1 in I. We can introduce a map P T0 T1 gamma from this tangent space into this other tangent space, writing P T0 T1 gamma of V is equal to the value of this vector field here, evaluated at T1. This map is linear because the system of ODEs is a linear system, and also an isomorphism because the inverse of P T0 T1 gamma is P T1 T0 gamma. So let's try to prove this theorem here. We have to handle two cases. The case number one is that is one where gamma I is contained in a single coordinate chart. So this means that we work with only one coordinate representation of the curve, and one let's write di and one local representation for the vector field V. Then V is parallel if a certain system that I raised of linear ODEs is satisfied, and if we use a theorem about the existence, uniqueness, and smoothness for systems of linear ODEs, it is immediate to get that there exists a V parallel along gamma such that V at T0 is equal to a given vector field, given vector V with T0 in I. And this solution is unique. The second case to handle is the one where gamma I is not covered by a single coordinate chart, and in this case we do the following. We define beta to be the maximum, the supremum, sorry, excuse me, of all b larger than t0, for which a unique parallel transport exists on T0b. Here I am making this choice. The argument I will use can be applied also in the case where b is smaller than t0. It is immediate to prove that beta is larger than t0, and the reason of this is that if b is close enough to t0, then the image of gamma t0b is contained in one single chart, and this means that we can apply the argument for the case number 1. So we have that this implies there exists a unique parallel transport V on T0 beta. We have to show that beta coincides with the supremum of the interval I. Suppose that this is not true. Then we work on an open set. Consider an open set containing gamma of beta minus delta, beta plus delta, where delta is a small number which is positive. The parallel transport exists on this interval, which is open on the right. So the idea here is that we construct the parallel vector field V tilde such that I want to write down the domain on beta minus delta, beta plus delta, such that V tilde at beta minus delta over 2 coincide with the value of V on beta minus delta over 2. The reason why I use delta is that I don't have the parallel transport on beta, at beta. But we know that V is unique. The parallel transport is unique, so V and V tilde must coincide on their common domain. V tilde V coincide by uniqueness on their common domain, and this means that we can extend V past beta, because V tilde is defined on beta minus delta, beta plus delta with delta positive. So V tilde is an extension of V past beta, and this means that we extended V beyond beta, and this is a contradiction with the definition of beta. Beta is been defined as the supremum of the value of the B of the parameter T for which the parallel transport exists. I want to say a word about the case where gamma is a piecewise smooth curve. Also, in this case, it is possible to define the parallel transport along gamma. So suppose that V is a piecewise, or maybe let's say that okay, let's start by this definition. V is a piecewise smooth vector field along gamma if V is continuous and there exists a partition, an admissible partition A0, A1, AK of I is the interval of definition of gamma, which in this case is supposed to be of this form, such that V restricted to a I minus 1 AI is smooth. V is parallel, V parallel if I should write along gamma, I think is clear. If dt V identical is 0, wherever V is smooth, that is on interval of this form. How to construct the parallel transport of V in T gamma A M along gamma in this case. This is the idea. You define the parallel transport V on A0, A1 as the parallel transport of V along gamma restricted to A0, A1. When you do this, you use the previous definition of parallel transport because a gamma restricted that on this interval is smooth. And then you define V on A1, A2 as the parallel transport of V evaluated at A1. And you continue this way. So then repeat this process. until you have covered the entire interval AB. Now I want to present one result which explains what is the relationship between the parent transport and the covariant differentiation. Vector field along gamma is the parent transport of a given tangent vector if the covariant derivative along the curve is equal to 0. But the following theorem says much more. Precisely, we have that the parent transport determines the covariant differentiation precisely if gamma is a smooth curve on M and V is a smooth vector field along gamma, then for each T0 in I, we have the following identity. This covariant derivative along gamma evaluated at T0 coincide with the limit as T1 tends to T0 of the parallel transport of V minus V at T0 divided by T1 minus T0. In order to prove this theorem, I need to introduce the notion of parallel frame along a curve. This is how this special frame is constructed. So given any basis B1, B2, Bn of T gamma T0 M, we can consider the parent transport of Bi along gamma In this way, we get E1, E2, En parallel vector fields along gamma. Since we know that the parent transport is an isomorphism, then we can conclude that E1t, E2t, ENT, this is a basis for this tangent space, and this basis is called parallel frame along gamma. Since they are parallel, it is true that T EI, this is identically 0, and this is a simple consequence. If I take a vector field along gamma, which is supposed to be, for example, smooth, then I can write it this way. Because this is a basis. And what is the consequence of this formula? The consequence of this formula is that this covariant derivative along gamma, it is equal only to Vi dot EIT. Remember that if you have the product f times x, where this is a function and this is a vector field along a curve, then this derivative here is f prime x plus f dtx. In this case, we don't have the sum containing the covariant derivative of the EI because it is 0. Okay, let's try to prove the theorem. If the 0 is a point in I, where I is the interval where gamma is defined, then I have that if V is a smooth vector field along gamma, I get immediately from this formula that dt v at t0, this is just vi t0 ei t0. Now let's consider t1 in I, and let's construct the parallel transport of Vt1 along gamma can we write down a formula for this parallel transport? Clearly, yes. It is Wt equal Vi T1 EIT. This is clearly the parallel transport of Vt1, because this is the parallel frame. And this says that Pt1 T0 gamma of Vt1, this is Vi T1 EI T0. Now, if I consider the limit as T1 tends to T0 of Pt1 T0 gamma Vt1 minus Vt0, and I replace this one by this in this formula, I get that this is just V dot I T0 EI T0 but this is V at T0. Sorry, but this coincides with what we wrote here. Clearly, here there is a typo because I forgot to write the dot symbol. So this is equal to dt v t0 Is a corollary we have that the parent transport determines the connection precisely. We have that if x and y are smooth vector fields on M. Once again, M can be a manifold with or without boundary. Then we have that nabla x, y at a point P. This is just the limit as h tends to 0 of parent transport P gamma h 0 of y along gamma h minus yp, where gamma is a smooth curve such that the initial point is P and gamma prime 0 is x at P. How to prove this? The proof is not difficult. Let's construct Vt as the vector field along gamma given by this formula, Vt equal y restricted at gamma t. This means that V is extendable and its extension is y. Then we can use a theorem about the definition, about the properties of covariant derivative along a curve and this theorem says that if you want to compute dtv, you can look at the covariant derivative nabla yx, where y is an extension of V and x is gamma prime t. So if you use this formula when t is 0, you have that this covariant derivative along a curve coincide with this formula evaluate this vector field evaluated at P, because gamma 0 is P. Now, a definition and a few results without proof. So definition I want to give you is that the definition of pullback connection. In order to give this definition, I want to recall what is a push forward of a vector field, of a smooth vector field on a manifold M by a diffeomorphism so push forward of X phi star X in T of M tilde. This is defined by d phi p x p equal phi star x at phi p. So what is the pullback connection? If nabla tilde is a connection in Tm tilde, phi is a diffeomorphism as before, then the pullback connection phi star nabla tilde is a connection in Tm and it is defined by this formula. It is necessary to prove that this is a connection. I leave the details to you. I want only to say that this connection satisfies some properties. Suppose that gamma is a smooth curve then we have that phi, which is this diffeomorphism here, takes covariant derivatives along curves to covariant derivatives along curves. Now, if you want to write down this statement using a formula, then we have to take a smooth vector field along gamma and consider its image by the differential d phi. Then it is possible to prove that this is d tilde t, d phi composed with v, where this is the covariant derivative along gamma with respect to the connection of M, and d tilde t is the covariant derivative along a curve with respect to the connection nabla tilde of M tilde. Statement B. Phi takes geodesics to geodesics. In other terms, if gamma is a geodesic, then phi composed with gamma is a geodesic in M tilde. This is a simple consequence of this formula here. Why? Use this formula with V equal gamma prime. Statement C. Phi takes parallel transport to parallel transport. If you want to write these using formulas, then for every T0, T1 in I, we have that d phi gamma T1 composed with P gamma T0 T1 this is P T0 T1 along phi composite gamma composite di phi gamma T0. Try to prove this result, which is a proposition, as an exercise. And now let's change topic. And let's talk about Levi-Civita connection. Let's start the presentation by making an observation about the Euclidean connection on Rn. The Euclidean connection Rn satisfies this formula nabla bar x of the inner product of y and z equal to inner product of nabla yx and z plus inner product of y nabla bar zx and y. This formula can be proved working with the standard basis. In general, this formula is not true for an arbitrarily chosen connection, so it makes sense to give this definition. A connection nabla in the tangent bundle Tn is compatible with the metric or is a metric connection if for each x, y, z in Q of M, nabla of this inner product is equal to nabla yx comma z plus y nabla y comma nabla zx. Let's present a proposition which gives us several ways of characterizing connections satisfying this property. So we have that the following conditions are equivalent. One, nabla is compatible with the metric G. That is, this is true. 2, nabla G is identically 0. This is something I will define later. This is the total covariant derivative of G, and it requires a definition because I am applying nabla not to a vector field but to a tensor. This condition is equivalent to say that G is parallel. So please wait a bit. Three. If E1, E2, En is a smooth local frame, then gamma KIL GLJ plus gamma KJL GIL, this is equal to EK GIJ for if PW are smooth vector fields along a smooth curve gamma then you have this very useful formula, ddt of this inner product equal to this sum. It's not finished yet. Five, if VW are parallel vector fields along gamma, then this inner product is constant along gamma. Six, every parallel transport map along gamma, where gamma is as before a smooth curve, is a linear isometry. We already know that it is a linear map. The novelty is that it is an isometry. And seven, every orthonormal basis at a point of gamma can be extended to a parallel orthonormal frame along gamma. I think that we will try to prove this result next time. Today I want to give the definition of I want to explain the meaning of this symbol. So I have to talk about covariant derivatives of tensor fields. We have the following proposition. In the textbook, you will find proposition 4.15, whose statement is quite long. I will present only the statements I need. So suppose that M is a smooth manifold with or without boundary, and nabla is a connection in Tm. Then nabla uniquely determines a connection in each tensor bundle TKL Tm, denoted by the same symbol, such that one in T10 Tm, which is equal to Tm, nabla agrees with the given connection so it makes sense to use nabla as a symbol. 2 in T00 Tm, which is possible to prove to be M times R, nabla okay, let's write just a formula. Nabla x of a function is just xf. This is a very useful identity. There are other statements that we will not use. I will only present this additional property for all f in gamma TKL Tm. So this is a section of this tensor bundle. So this means that this is a tensor smooth covectors In the textbook, instead of the word covectors, you will find the word one form. If you took the course Differential Geometry for graduate students, you know what a one form is, but it's enough to know what a covector is. So for smooth covectors omega 1, omega 2, omega k, and smooth vector fields y1, y2, yl, we have that excuse me, it is possible to give a meaning to nabla fx. This is defined by this formula. There are three kinds of summands. The first one is x of f omega 1 omega k y1 yl. The second is preceded by a symbol minus, f of omega 1 I don't have enough space, so I have to write and the last kind of summand is f this. And now I want to present without proof another proposition which defines the total covariant derivative so for every f in gamma t k l t m that is a tensor, the map nabla f defined by this formula where these are covectors and these are smooth vector fields given by L, is a smooth K L plus 1 tensor field on M called total covariant derivative I want to show a special case f equals g, a metric so the total covariant derivative of the metric tensor G is given by this formula, which follows from the previous formulas: x, g, y, z minus g nabla yx minus g y nabla x z. I agree with you if you are thinking that this is quite complicated to understand, but at least this special case I think it's clear. Let's stop here. Thank you for your attention.